we've gone through subtopic 10.1 on describing fields, looking at electric fields. We're now going to go back through and have a look at gravitational fields. Now this should be fairly straightforward given that we've got electric fields that we can compare to. So the first thing to note here is that when we are looking at gravitational fields, these concepts of potential and equipotential surfaces, they can be transferred to gravitational fields quite easily. So once we've got an understanding of what those ideas are in electric fields, it's simply just a matter of changing perspective a little and identifying what it is that's similar with gravitational fields but also different. So those ideas, as I said, are easily transferable. And in order to sort of transfer them across, what we're going to do is compare what we've seen with electric fields and look at the gravitational equivalent. So the first scenario is to look first of all at what happens with a negative charge. The reason why we're dealing with a negative charge, you'll see in a second, is to do with the gravitational field itself. So with a negative charge, we see that the field lines go towards the negative charge, and that means that we've got a radial field. Let me just note up here that this is for electric fields. So that's a radial field, and if we consider what happens with gravitational fields, we can see that gravity or gravitational fields look very similar to electric fields with a couple of differences. So the first thing is that we're now dealing with mass. With a mass, we get that these field lines, the gravitational field lines, are likewise directed in towards the mass. So, like I said, similar to a negative charge. Now, we don't have a comparison for a positive charge, because gravity is always attractive. It's going to resemble a negative charge, not a positive charge. So there's the first similarity. Secondly, if we then look at a uniform field, so we had this situation with with charges. If we had, say, positive charges across the top and negative charges across the bottom, and the way that we'd set those up is by connecting them to some sort of power supply or an EMF. The field lines there would be directed from the positive to the negative, going downwards. Now, for a uniform field, for a gravitational field, slightly different. Imagine that we're just considering one tiny spot on this particular mass that we've got here, and we're sort of going to blow that up into a much larger image. We could think if we get really close to the surface, it's going to look close enough to being flat. Much the same as when you look across the surface of the Earth, when you're standing on it, it appears generally pretty flat. But when you get further away, you can see that the Earth is actually more spherical in shape. So for a gravitational field near the Earth's surface, the field lines are likewise a uniform field. So note that I've changed the orientation of that field so that we can represent what it looks like from the perspective of being on the Earth itself. So you can see that those two ideas, or those two field shapes, are very much the same, whether it's a gravitational field or an electric field. That means that if we then look at equipotential surfaces, we did made a few notes about equipotential surfaces for electric fields. We're going to just sort of, I'm going to cheat here a little bit and just cut and paste those so that we can just change them slightly where we need to. So if we look at equipotential surfaces, so this is the wording for electric fields, we need to change a few words here. So first of all, equipotential surfaces now will link points that have the same gravitational potential. They should refer to a zero potential. Here we've got that it should be the negative plate in the previous example we were looking at. We're just going to remove that, and we'll talk about what the zero potential is for gravitational fields later, not necessarily at this point. That next point there then is that regions where no work is done is when the charge is moving along the surface. Now for gravitational fields, we're looking at mass moving along the surface. The equipotential surfaces are at 90 degrees to electric field lines. Again, we need to change that to gravitational field lines. Last couple of things there, we have that equipotential surfaces as scalar quantities, and likewise they can never meet equipotential surfaces with a different potential. And so those ideas are similar across the two, whether it's gravitational fields or electric fields. If we go then to look at electric potential, we have a similar sort of comparison that we can make. So starting off for electric potential, the equation that we looked at there, more importantly, we're looking at potential difference. We'll deal with electric potential and gravitational potential in more detail in the next video. But if we look at not in the next video, in 10.2, if you look at what the potential difference is in an electric field, that was equal to W on Q. So that then means that the work that you're doing is equal to Q times VE, delta VE. So change in the potential in an electric field, and then we can figure out what the work would be done in an electric field. So for gravitational fields, again we can see there that with electric fields we're interested in charge. For gravitational fields, or gravitational potential difference, we're not interested in charges, we're interested in masses. And so the quantity that we're dealing with now is delta Vg for gravitational fields. It's still going to be work, but it's now going to be divided by mass. So for a gravitational, the work done against a gravitational field would be equal to mass times the change in gravitational potential. Now that equation is an important one, so I'll just highlight that. I'll go back and highlight this one as well. That's another one that's in the data booklet, but you will have already jotted that down from earlier videos from subtopic 10.1. One last thing here, another common idea between these two. Since work is only done moving against the field, so we're having a look at this idea of where the reference point is for gravitational potential. Work is only done when moving against the field, so in the opposite direction to the field lines. That means that we can use that to identify where the zero potential is for gravitational fields. So in this particular case, we're really looking at doing something like lifting an object. So if an object falls, we're not doing any work on it. In this scenario, we're looking at doing work, so we have to actually work against gravitational field lines. And so that then means that we have the zero potential, so Vg. You'll note here too, I should have mentioned earlier, when we're looking at potential difference, that means that we're using units of joules per kilogram, so we can get that from this equation here. So the units there, we don't rename them, whereas electric fields they're volts. For gravitational fields we just leave it as joules per kilogram. So that zero reference point of 0 joules per kilogram, that's going to be at infinity. So you need to get a very large distance away from a mass in order for the electric potential to be zero. Gravitational potential to be zero. So if we go back again and have a quick look at this scenario where we've got our mass m with gravitational field lines around it, somewhere all the way out here at infinity we would have Vg being equal to 0 joules per kilo. Now if we had a point in here somewhere, let's call that point A, then the potential there might be, say, something like 10 joules per kilo. So that means that for every kilo of mass we've had to do 10 joules of work on it to get it to point A from infinity. Sorry, it should be negative 10, getting closer. And then if we go even closer again, then B is going to be negative 20 joules per kilo. So by coming closer we would have to then effectively do more work to drag that mass out to infinity. The potential difference between those two then would be given as, depending on which way you move, if you're going from lower to higher or higher to lower. So the potential difference there would be 10 joules per kilogram. So there's some ideas that we can see where we can see a link between electric fields and gravitational fields. We'll continue that in 10.2, having gone through all of the electric field concepts there as well.